matter, and we ended up creating a directional bias for charges. We maintained the ends of this conductor at constant potentials and ended up creating a uniform electric field E, let's say from left to the right. There was a current associated with the cross section. If this was any cross section, then across this cross section, a small amount of charge dq passed in time dt, resulting in a current I through this cross section, right? And we also defined a current density associated with this cross section. If this cross section had area A, if A was the area of cross section, then we defined J, which is current density, as I by A, which is like 1 by A, I written as dq dt, right? So I can say from left to right, a small amount of charge dq would have flowed in a small time dt through this cross section. Positive charge from left to right, or the same amount of negative charge from right to left, right? And if the drift velocity of electrons was vd to the left, if the drift velocity of electrons was vd to the left, then the drift velocity of an equivalent situation, positive charges, would be vd to the right, right? There would have been a drift velocity vd to the right of positive charges, right? Vd is the drift velocity. Now, if this piece of matter had n electrons per unit volume on an average, electron density, n electrons per unit volume, then there would be a charge Ne per unit volume. E is the charge on an electron, right? There would be a charge Ne per unit volume, and the same amount of positive charges in that volume, right? The same amount of positive charges in that volume. So now what I do is, say in a small time dt, an amount of charge dq flowed through this cross section. In a small amount time dt, a small amount of charge dq flowed through this cross section, right? And this dq, let's say, covered dx in that time. This dq covered dx in a time dt. Dx obviously would be covered at drift velocity. Yes or no? If dx was covered by charge dq, then it would be done at drift velocity. Now, the current density, like I said, would be current divided by area of cross section. That's the current density, right? Which is like 1 by A dq dt. Yes or no? And all the charge that would have flowed out of this cross section in a small time dt would have occupied this space. All the charge in a small time dt that would have flowed over a length dx would have occupied this volume? Would have occupied this volume, yes or no? So that charge dq that would have flowed through this would be contained in this volume. This dq would have been contained in this volume. Now, how much of charge would be contained in this volume? Charge per unit volume would be any into the volume of this region. Volume of this region is ADX. Volume of this region is ADX. Volume of this region would be ADX. That's the charge contained in this. So what I do is I write this as 1 by A. dq I can write as NE ADX. Hey, but dx dt must be drift velocity. Dx dt must be drift velocity. So this is A getting cancelled. This is NE and dx dt is Vd, the drift velocity. NE Vd. That's the current density. So that's the relationship between current density and drift velocity. Current density and drift velocity. Current density and drift velocity, that's the relationship. J would be NE into Vd. Now, for certain kind of conductors, under certain stipulated conditions, not always, there is a lot of if and but about my next statement. If there is an electric field E and the potential difference between the ends is V, if there is an electric field E and there is a potential difference V over a length L, potential difference V over a length L, then can I not say that E would be V by L? This is what we have learnt in electrostats. E would be V by L, right? Drop in potential over the length. That's going to be the electric field from left to right that I've created. So, E is a consequence of V. I have handle over V. There can be a mechanism by means of which I can maintain a potential difference V across the end, and this is what it results in terms of the electric field across through the cross section along the length, I mean. Now, again, like I said, in a tremendously restricted sense, for certain kind of conductors under certain conditions, the current flowing through the cross-sectional area, the current flowing through the conductor across various cross-sections under steady-state conditions is going to be proportional to the potential difference across its ends. Not all conductors will enjoy this characteristic. Conductors that enjoy these characteristics are called ohmic conductors. Conditions under which this happens, they are called ohmic conditions. Such conductors which enjoy this are called ohmic conductors. And there are ohmic conditions. One thing, of course, I have to maintain the temperature constant. At a given temperature, if I am carrying out this experiment, for ohmic conductors, at a given temperature, if I am carrying out this experiment for ohmic conductors, if I double V, I will get double. If I triple V, I will get triple. If I half V, I will get half for a given conductor. Called an ohmic conductor. At a given temperature, you don't vary the temperature. At a given temperature, for a given ohmic conductor, if I keep varying V, then I will vary in a manner that I will be proportional to V. Again, there is not a guarantee that every conductor, once ohmic, will always be ohmic. May not be ohmic always. At the same conductor, if I operate at higher temperatures, will not show a proportionality between current and voltage. Will not show linearity between current and voltage if the same conductor, for the same conductor, essentially ohmic at that point of time. If I elevate the temperatures, then it is possible that at higher values of temperature, it ceases to respect the linearity or proportionality between current and voltage. So there is a lot of limitations around this condition. One, it must be carried out at a constant temperature for a given conductor. If I, then current will be proportional to V. Semiconductors will not enjoy this linearity between current. Thyristors, there is another variety of electrical entities that we will look at. They will not enjoy. Diodes we will look at. They will not enjoy current and potential difference linearly or proportionally related. So then, like I said, there is a host of conditions that are associated with this. But then, I'm talking of ohmic conductors and ohmic conditions. Ohmic conductors and ohmic conditions, in which current will be proportional to the potential difference applied across the ends. And for such conductors under such conditions, there is this constant of proportionality which is designated by R. Designated by R. R is such a property that if I increase R, then for the same V, I'll have lower I. On increasing R, for the same V, I'll have lower values of I. You know what I'm saying? That means this is averse to flow of current. It opposes current. R is a property which opposes current. Yes or no? Because, do you realize that? For the same V, if the value of R is increased, then I will decrease. Right? So, bulkier the value of R, the smaller will be the value of current for a given V. Now, this V has nothing to do with the matter. This V is about an external mechanism. And this is an external mechanism producing that V. So this has nothing to do with the conductor and its properties, right? I have handle over this, right? But I don't have handle over this. It will depend on R. So R is a property of the conductor, essentially a property of the conductor. And it's called the resistance. It's called resistance. This R is referred to as resistance. And is measured in SI units, ohms. This is the symbol, ohms. Right? The value of R will depend on two things. The resistance of a conductor will depend on two things. This is my conductor. One, its geometry. To the material of which it's made of. I could have had the same geometry, same length, same area of cross section, made out of copper, made out of steel, made out of aluminum, right? With the same geometry, but I use different materials, I get different values of R, right? So R will depend on geometry and will depend on material. It's called resistance. Yes, it does. In fact, for certain materials, we'll be able to show that R at a temperature T is R0 into 1 plus alpha T. There is, yes, it does depend on temperature. to a certain extent weaker function. Weaker function, not a very strong function of pressure. Again, depends on what pressure. We are talking of solids. So pressure is not that important. It's a very, very weak function. It's primarily a function of temperature. That's all right. Acupressure. All right. So this R, it was found out of experiment, and you know there is no model around it, just out of experiment. This R is found to be, for a given conductor of length L and area of cross section A, this R, you would have read in junior class also, is like a constant rho into the length L divided by area of cross section A. That's the resistance R. That's the resistance R. L and A are geometry related factors. Rho will depend on the material. Rho will depend on the material. This rho is called resistivity or specific resistance. Is called resistivity, and it will depend on the material. It will depend on the material. It's called resistivity and will depend on the material. Copper will have one value, steel will have another value, aluminum will have a third value, and so on and so forth. So this is the material, and L and A are geometry factors. Sometimes it's also called specific resistance. Sometimes it's also called specific resistance, right? And 1 by rho is denoted by sigma and is called conductivity of the material. Is called conductivity of the material. 1 by rho is denoted by sigma and is called conductivity. Now, having said this, let's come down to this. Right? V is I into R. V is I into R. Potential for ohmic conductor under ohmic conditions at a constant temperature. V and I are linearly related. This is resistance of the conductor that I am dealing with for the experiment. Ohmic conditions, like I said. Temperature constant, no. There is again, property of that matter. It will not allow linearity. Like I said, there could be thyristors, there could be semiconductors, there are current associated, but it will not be proportional to the voltage that I apply. Then there are diodes. I do not know if you have read Child-Langmuir law, where current is proportional to, a different power of voltage. So again, there are conductors that are inherently not even ohmic. So that's a property of conductors. They will not allow linearity. Thyristors, semiconductors, and so on and so forth. Right? So now, V is I into R. I into R. This R I can write as rho L by A. V by L is I rho by A, right? V by L is the electric field. V by L is the electric field. Yes or no? This V by L is the electric field E that's applied, right? And I by A is the current density, I by A is the current density J into rho. This I by A I replace by J, the current density into rho, right? Then I end up getting the current density in terms of the electric field as E by rho. Current density as E by rho. E is the electric field applied, rho is the resistivity of the conducting material. And this can be like E into sigma, because 1 by rho is sigma, the conductivity. So that's another relationship you want to remember. Another relationship you want to remember. So one of the things, if there is a current I flowing through a conductor. Now you can call it a resistor also. It has a property called resistance. It has a property called resistance. You might call it a resistance as well. So, if there is a current I flowing through a conductor, then in the direction of the current, there is a drop in potential, which is I into R. There is a drop in potential across a conductor, which is I into R, which is the resistance, right? Now, so far so good, right? Not an issue. So, if this was a resistor or a conductor, I want a current to flow through this. I want a current to flow through this. What must I do? I must maintain a potential difference across its ends. I must maintain a potential difference across its ends. The mechanism that helps you maintain potential difference across the ends of a conductor is called a battery. A battery, as you know, I don't know if you do, but it has a positive terminal, a negative terminal, the cathode, the anode, and between the cathode and the anode there is an electrolyte sandwiched. There is an electrolyte sandwich. There is goddamn chemistry going on there. We'll not bother about the chemistry in this class, right? There is a chemical cell, essentially, right? But in principle, all batteries, have the same principle. There is a cathode, there is an anode, and there is an electrolyte, right? But forget about all of that, put all of that in a black box, at least for the time being. Symbolically, to maintain a potential difference, what I do is, there is a positive terminal of the battery, it is designated by plus. And there is a negative terminal of the battery, a minus. And there is a chemical mechanism here that maintains this terminal of the battery at a higher potential compared to this terminal. There is a mechanism going on inside the battery which will maintain this terminal of the battery at a higher potential compared to this terminal of the battery, right? So I connect one end to the positive terminal of the battery, the other end to the negative terminal of the battery. There is a potential difference across the terminals of the battery called V. There is a potential difference across the terminals of the battery, call it V. This V is also called the EMF of the battery, electromotive force, EMF of the battery. It's also called the EMF of the battery. And to begin with, looking at a battery which does not have, for instance, what is called an internal resistance. That means when there is current flowing between the poles of the terminals of the battery, there is no resistance. I'm assuming that it's an ideal battery. And V is the EMF available to the battery because of its mechanism. So that mechanism maintains the potential difference between these two terminals as V volts. That means if I look upon this as 0 volts, then this will be V volts. It's the potential difference which is important, not the absolute potential. So what this means is this is lower potential, this is higher potential. If this is referred to as 0 volts, this should be referred to as V volts. Right? This is what it means. Now, electrically, this is the same as this, and this is the same as this. That means if this is 0 and V, these ends will be 0 and V. Right? So there is V volts drop across this, and there is V volts increase from here to here. What happens is that there is a current I initiated into the conductor or the resistance. There is a current I because I maintained a V. I maintained a V, there is a current I initiated. There is a current I that starts to circulate. This is the simplest model of a circuit that we could have. There is a resistance I associated with it. Right? Now, this is a full loop. 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 This battery sets up an electric field. Sets up an electric field like this. This sets up an electric field E like this. From left to right, there is going to be an electric field set up by the battery because of the potential difference. Inside the battery, this is the positive terminal, higher potential. This is the negative terminal. The electric field is in this direction. The electric field is in this direction. Do you realize that? Electric field across the resistance conductor is like this, whereas between the terminals, the electric field will be from positive to negative. Yes or no? There is, then, if I traverse the entire loop, this is a full loop. This is a full loop. Then, from here to here, there is a potential. So what we'll do is conventionally, drop of potentials we'll take as positive and increase of potentials we'll take as negative. So we'll take drop of potentials in any loop as positive and increase as negative. Drop of potentials is positive, increase of potentials as negative. So if I traverse the full loop and I take algebraic sum of the drops across the loop, right? I'll take algebraic sum of the drops across the loop. In the full loop, if I take algebraic sum of drops in the full loop, right, there is V like this, drop. And then I go from here to here, there is minus V, there is increase. From here to here, there is V volts decrease. From here to here, there will be V volts increase. So I'll take negative, right? So obviously, as you would expect, algebraic sum of the drops across a loop is always 0. This is a very simpler version of an electrical circuit. No matter what, at any given instant of time, the algebraic sum of drops across various entities in a electrical loop will be 0. Algebraic sum of drops will be 0. Electrical forces are doing positive work here. When positive charges are moving from here to here, electrical forces are doing positive work. Yes or no? Electric field is like this. Electrical forces will do positive work. When positive charge moves from here to here, the electric field is like this. But the charge is moving from negative to positive terminal. So work done by the electric field will be negative. You realize that? Shall I repeat what I've said? I'll repeat. See, after all, when I talk of current, what am I talking of? Conventional current. Conventional current is what? Flow of positive charges. Flow of positive charge. So when positive charges flow from here to here, this is the direction of the electric field. Work done by the electric field is going to be positive because they experience force in this direction, they displace in this direction, right? But Let's say, so there is a positive charge Q which comes from this point to this point, right? What is the work done by the forces of the field? Q into V. That's the work done by the electric field. E is going to be Q into V. Yes or no? Isn't it? Q into V. But, right, positive work done by the electric field here. But when it goes from here to here, the electrical forces are in this direction, because the electric field is like this. From positive to negative will be the electric field. Isn't it? Electric field inside the battery. This is the inside of the battery. This is the inside of the battery. Right? Inside the battery, the electric field will be like this. So when this charge Q comes to this point, it has to go against the electric field. It experiences a force because of the electric field in this direction, but it gets displaced in this direction. Yes or no? So the work done by the electric field will be negative, and the positive work done by the electric field balances the negative work done by the electric field here. The algebraic sum of the work done by the electric field is 0. The algebraic sum of the work done by the electric field is going to be 0. Right? Positive work done here and negative work done here. So okay. Think about it like this. From here to here, positive work done, right? The charge, when it comes here and goes there, work done is Q into V, from higher to lower potential. The same charge, 0 to V, increase in potential, work done then negative, minus Q into V. So plus Q into V and minus Q into V must add up to 0. Yes or no? Does it make sense? Now, look, when this charge, please understand this fact, huh? When this charge goes from here to here, positive, I'm talking of positive charge again, because I'm talking of conventional current, right? So when this charge goes from this end to this end, when this charge migrates from this end to this end, its potential is decreasing. It's losing energy. It is getting depleted in energy. Yes or no? When this charge is going from this end to this end, it is depleting in energy. It's losing potential energy. Yes or no? By the time it comes to this point, right? By the time it comes to this point, now to go to this point, its potential must increase. So it must be energized. This charge would have to be energized. To go from lower to higher potential, it must be energized. Yes or no? And if it is energized, there is something that must energize it. Something that must energize it. It is that battery mechanism that energizes the charge. You know, from here to here, there is drop in potential. The charge de-energizes. It loses energy. Right? It loses energy. It's going from higher to lower potential. It's losing energy, right? And by the way, you might be tempted to think, hey, is it getting converted into kinetic energy? No, it's moving with drift velocity. So kinetic energy is remaining the same. It's moving with drift velocity. So kinetic energy is remaining the same, because it's not moving unimpeded. There are umpteen collisions during the process. And the net of all of this is a constant, almost a constant drift velocity. So kinetic energy of charges is not changing. Right? There is a drift velocity. So that does not change. So what is happening from here to here? It's getting de-energized. Its potential energy is decreasing. So by the time it comes here and you want it to circulate through the loop one more time, you must raise it from lower potential to higher potential. You will have to energize it. You would have to energize it. That means something must provide the energy. Something must provide. It is the battery which provides that energy to then listen to this charge. When it arrives depleted, after having made its passage through this resistance, it arrives depleted at this terminal of the battery. To move it to a higher potential, you would have to subscribe energy to this charge. It is the mechanism inside the battery that gives it the amount of energy to make its passage, and then once again It's robust. Once it arrives at the positive terminal, it has enough energy to circulate through the loop. Lose that energy through this resistance, through this conductor, come back depleted again, request the battery to provide more energy, comes to the positive terminal, higher energy levels, ready to circulate through the loop one more time, and this process continues. Yes or no? Do you understand the mechanism of this flow, the mechanism of this circulation? Right? And realize then that so algebraic sum of the drops in a closed loop must be 0. Algebraic sum of the drops in the closed loop must be 0. So the drop from here to here is IR. Yes or no? The drop from here to here is IR. And then I come back here. From here to here, there is a negative drop because there is an increase. So minus V. That must be 0. Right? This essentially, algebraic sum of drops in a closed loop being 0 is called Kirchhoff's voltage law. Is called Kirchhoff's voltage law. नहीं समझ में आया क्या? नहीं समझ में आया? नहीं आया? Properly. This is KVL. This essentially is KVL. Algebraic sum of drops in a closed loop must be 0. That's KVL. That's KVL. Kirchhoff's voltage law. We'll call it KVL. It's as simple as this. I could have had. So a common way to designate a resistor element is this. This is R. This is R, which is a resistance. Sometimes we call it a load. Sometimes we also call it a load. We sometimes also call it a load. Right? So then if I have, say, an electrical circuit like this, there is one load, resistance R1, there is another load, resistance R2, and I'm talking of an ideal battery to begin with. There is a battery of EMF epsa 1 like this, there is a battery of EMF epsa 2 like this. This is an electrical circuit. This is an electrical circuit. This time there are two batteries, one of EMF epsa 1, one of EMF epsa 2, with their polarities as shown, right? And if I want to find the current through the loop, then I assume that the current is I, right? And I apply KVL to the loop. KVL to the loop means what? Algebraic sum of drops must be 0. When a current flows through a resistance, there is a drop in voltage. The drop in voltage is current into resistance. That's the drop in voltage. That means from here to here, across this resistance, the drop is going to be IR1. Again, from here to here, across this resistance, the drop is going to be IR2. Yes or no? So then, I'll take all drops as positive, all increase as negative. So there is IR1 drop plus IR2, another drop, and then from here to here there is a drop, epsa 2. Epsa 2 is the drop, so plus epsa 2, and then from here to here there is an increase by epsa 1. Nahi kya? So increase is negative, minus epsa 1. This is the algebraic sum of the drops in a closed loop. Please make sure you understand that. Don't feel shy if you are not able to comprehend one or more elements. Please understand, these are not things you can miss out at all. This must be 0. That's KVL applied to the loop. That's KVL applied to the loop. This will enable you compute the current. This will enable you compute the current I, applying KVL to the loop. It's based on the fact that the algebraic sum of potential drops in a closed loop must be 0. Algebraic sum of potential drops in a closed loop must be 0. It's part of the fact part of the narrative that the work done by an electric field in a closed path must be zero. Conservative field. Work done by the electric field in a closed path must be zero. It's a conservative field. It's just a statement akin to currents now. Just applied to currents. It's that very statement, a property of conservative fields that I have deployed now for an electrical circuit. Okay, so like I said, I'll take algebraic sum of the drops in a closed loop as 0. The drop here is IR1 in the direction of the current drop. In the direction of current drop, IR2, right? Now from here to here, there is a drop. Because positive to negative means there is a drop. So I'll take positive, so plus epsilon 2. But from here to here, that's a full loop. I'll have to cover the entire thing, right? All elements of the loop would be covered so as to call it a full loop. And from here to here, there is an increase. So increase negative. Minus epsilon 1. Yes or no? Clear? Don't feel shy to ask. Yes, will depend on epsilon 1. If I turns out to be positive, then this is the direction of flow of current. If I on solving this turns out to be negative, then the direction of current is like this. Yes or no? So this is talking about an ideal battery. This is talking about an ideal battery. Huh? Now, see, if this is a load, a resistance R, and a current I flows through this, right? So, essentially, you know, if there is a charge Q that goes from here to here, if there is a charge Q that goes from this end to this end, it gets de-energized. It loses energy. How much energy does it lose? It loses energy Q into V. That's the energy that it loses. That's the energy that it loses, right? V is the drop in potential. What is V? V is I into R. V is I into R. So the energy lost by this charge and going from here to here is Q into V. Is Q into V, right? It loses potential energy. It loses potential energy. Now, so this is like Q into V, which is IR. That's the energy lost. That's the energy lost, right? That's the energy lost. That's the energy lost, E. Now, rate at which it loses energy. Rate at which it loses energy is dE dt. That's the rate at which it loses energy. I and R are constants. So this is like IR dQ dt. That's the rate at which it loses energy. But dQ dt is what? I. dQ dt is I. So this is like, if I replace dQ dt by I get this as I squared R. That's the rate at which it loses energy when it passes through a resistance R with a current I associated with it. Do you understand this? That's the rate at which. Okay. See, when this charge, imagine a charge Q going from positive terminal to negative terminal, part of this current. What is the amount of energy that it loses? Q into V. Q into V. V is IR, right? Rate at which energy is lost? IR into dQ dt. But dQ dt is I. So that makes it I square R. That makes it I square R. I can be written as V by R. I can be written as V by R. So that's also V squared by r. That's also v squared by r. Right? Hey, now question would be, it's losing, this is the rate at which energy is lost. This is the rate at which energy is lost. That means these many joules per second is lost. These many joules per second is lost. Energy lost per unit time. This is energy lost per unit time, which is now the power associated with this. That means the power that this charge is giving away. After all, you know, I'm not a mad guy, or scientists were not mad to unnecessarily make things flow. You know, if this energy is lost, it's lost with a constructive objective. It's lost with a constructive purpose. It has to be made available somewhere. This energy is made available to the load, for example. In this case, this energy is actually energy dissipated as heat. This is energy dissipated as heat. Right? So in heating coils, that heat that you see is the I square R heat generated. That's the I square R heat generated. There could be incandescence, there could be light also generated. Depending on R, there is heat generated, and so on and so forth. Obviously, if too much heat is generated, if I is very large and R is also large, then I square R will be large, and then, you know, it will lose its ohmic properties. It will lose its ohmic properties. You don't want too much heat to be generated. So, you should know where to stop. As an electrical engineer, you should know that if I want linearity between V and I, this is my quiescent point. I must stop here. Otherwise, I'm going to create a very complicated I versus V model, and I'm going to find it difficult to handle. So I want, by and large, you know, when electrical designers work on electrical circuits, they want to work on linear conditions, because linear conditions are mathematically simpler to handle. Non-linear conditions will be complex to handle and manipulate, but linear conditions. So if you create dealing with too high a current, if you're dealing with too high a current, you generate too much of heat, and if you're generating too much of heat, then the temperature of this goes disproportionately high, and if the temperature of this goes disproportionately high, you run the risk of making this otherwise ohmic conductor a non-ohmic conductor. The linearity between I and V will get dissolved. Yes or no? Right? If you restore it to a lower temperature, once again, it will oblige. Right? So that's joule heating. That's the joule heating through a conductor. These many watts or joules per second. These many watts or joules per second. Yes or no? And what's the source of this energy? Obviously, the mechanism inside this battery is eventually the root cause of this energy. That is where this energy comes from. Right? Obviously, you know, this battery cannot provide you this energy all the time. Eventually, it will get depleted because of a certain chemical reaction. There would be saturation conditions reached, and we then say that the battery is discharged. We then say that the battery is discharged. Now, so far so good. Not an issue with these rudiments, right? Also, there could be several electrical circuits, and there could be a junction of several electrical circuits, J. There could be a junction J, common to several electrical circuits, common to several loops, there could be a junction J, right? And one loop is sending current I1 to J, another loop is sending current I2 to J, a third loop is sending current I3 to J, a fourth loop is sending current I4 to J, a fifth loop is driving current I5 away from J, and so on and so forth. So there would be, because of several electrical loops, several electrical circuits, there could be currents coming into the junction, there could be currents leaving a certain junction. A junction is an electrical point. A junction is only an electrical point. So there could be currents coming into the junction, there could be currents leaving that junction. The important thing is current will not accumulate at any given junction. Current will not accumulate at any given junction. The net current coming in will be equal to current leaving. All the current that comes into a junction must leave that junction. It has no room to have residence in that junction under steady state conditions. Under non-steady state conditions that will transpire, but we are talking of steady state conditions. At a given junction, all the current that comes in must be equal to current leaving. So what is the current coming in, for example? I1 plus I2 plus I3 plus I4, and say I5 is one current leaving and I6 is another current leaving. So all the current that enters is equal to current that leaves, I5 plus I6. Current entering equals current leaving. Current entering a junction equals current leaving that junction current entering the junction equals current leaving the junction, because there cannot be any accumulation of current at a given junction. And this principle is called Kirchhoff's current law. Kirchhoff's current law, which is KCL. Kirchhoff's current law, which is KCL. No, why? Why should they be equal in magnitude? No, sab alag ho sakta hai. They can all be different, right? Yes, because they are an outcome of a conservative electric field only that we are creating out of a battery mechanism. So this is just a restatement of charge coming in is equal to charge leaving, because there is no accumulation of charge, anywhere. Yes or no? No confusion, right? All of you understand this perfectly well. Very good. So we have learnt Kirchhoff's voltage law, we have learnt Kirchhoff's current law. Now, see, when I talk of an ideal battery, this is an ideal battery of EMF EPSA. EPSA ideal battery. Because when the current I was circulating through the loop, on its arrival at the negative terminal, it was made to pass to the positive terminal. It had to flow through this. Right? We are assuming that this current in its passage from negative to positive terminal did not encounter any resistance. That's an ideal battery. It did not encounter any resistance. That's an ideal battery. But in a real battery, this region itself will pose a resistance small r. For the current I, this itself will pose a resistance small r. That's a real battery. A real battery is essentially then superimposition of an ideal battery, EPSA, and an internal resistance small r. This small r is an internal resistance. This is an internal resistance. So, if I'm talking of a circuit like this, then this battery could have, which was an ideal battery, which was a real battery, could be replaced by an ideal battery and an internal resistance small r. This is the scenario. This is the scenario. Right? Now if I have to find the current through the loop, then I apply KVL to the loop. Then I apply KVL to the loop. Now when I apply KVL to the loop, I get I into R, drop across this, right? Then current comes here. There is a drop across this small r, which is I into small r. Then from here to here there is an increase, so minus epsa, right? That must be 0. Algebraic sum of drops must be 0. So that gives me I equal to epsa by capital R plus small r. Yes or no? Right? And now, where R is the internal resistance of the battery, right? The power associated with the load, like I said, is going to be I squared capital R. The power associated with the load is going to be I square capital R, which is epsa squared by R plus small r whole squared into capital R. Yes or no? That's the power associated with the load. Yes or no? I written as epsa by R plus small r. Clear? Now, so these many watts are dissipated across the load. These many watts are dissipated, or this is the energy available at the load, no matter what, where you want to use that. This is the energy dissipated or available when current flows through the resistance R. And now this I can write as epsa squared divided by R squared plus 2RR plus R squared divided by capital R. Yes or no? This is epsa squared divided by R plus R squared by capital R plus 2R. Yes or no? Yes or no? Clear? Now, sometimes our objective of driving the current is to maximize the power output here, I want to maximize the power output here. I can't do anything about the battery. I am already given a battery, epsa and small r. So there is epsa and small r are constants. Epsa and small r are constants. I can't do anything about the battery. But I have a resistance box from where I can choose my resistance. I can pick my resistance, capital R. Now what is it that I want to do? I want to pick a value of capital R that will maximize P. This is the model that I want to create. What am I trying to model here? Pick R for a given battery. When I say given battery, that means given epsa and given internal resistance. I can't do anything about the epsa and internal resistance of the battery, but I have control over the load R, capital R. I now want to select a value of capital R. That will maximize. Pick R for a given battery such that the power across the load is maximum, such that the power across the load is maximum. This is how I want to select my capital R. And I have no handle over small r. Now, look, if I, can I remove this part? Can I remove this part? Okay. So, I want to have P equal to P max. Right? Now, if power is maximum, then the denominator must be the minimum it could be. I have to select the smallest possible value of the denominator so that the ratio is the largest, right? That means I want to minimize r plus small r squared by capital R plus 2r. I want to minimize this. Then the ratio will be maximum. Power will be maximum if I minimize this. Yes or no? Is that okay? Now, I can't change this. 2r, I can't change this. That means essentially I have to minimize r plus r squared by capital R. Because 2r I can't change, it's related to the battery. But this expression I can change. I have to minimize this. R plus r square by capital R I have to minimize. Now, r plus r squared by capital R by 2. That's the arithmetic mean of these numbers. That's the arithmetic mean of these numbers. And that must be greater than or equal to the geometric mean between them. Root r into r squared by capital R. Yes or no? AM greater than or equal to GM. That means r plus r square by capital R is greater than or equal to 2r, is greater than or equal to 2r. That means the minimum value of r plus r squared by capital R is 2r. That's the minimum value of this. That's the minimum value of this expression, yes or no? Right? And it happens when this becomes equal to this, that means when AM becomes equal to GM. It happens when AM becomes equal to GM. And when would AM be equal to GM? When the quantities involved in their constitution are equal. When the quantities involved in their built up are equal. This happens when AM equal to GM. And this happens when R becomes equal to R square by capital R. When R becomes equal to R square by capital R. That means when capital R becomes equal to small r. Yes or no? That means power will be maximum if the external resistance R is equal to the internal resistance of the battery. Power dissipated across a load will be maximum when the load selected is equal to the internal resistance of the battery. When the load selected is equal to the internal resistance of the battery. You have knowledge of the internal resistance of the battery, select the load. So it depends on the situation. It's not like this is always the objective, but some cases this is my objective. If this is my objective, then I rather select the value of capital R matching with small r. Then I will have maximum power dissipated across the load. Right? And when so maximum power would be when capital R is equal to small r. So put capital R equal to small r. What do you get? Epsilon squared by 4r squared into small r. Put capital R equal to small r. So 4r squared into small r, which is epsilon squared by 4r. That's the maximum power that could be dissipated. Epsilon squared by 4r is the maximum power that could be dissipated. Now, let me draw the power versus capital R. If I vary capital R, I know that when capital R becomes equal to small r, power is maximum. Power dissipated is maximum. But let me have a rough idea of the variation of power with small r graphically. Right? And by the way, this condition is called the maximum power theorem. Maximum power theorem. This is called maximum power theorem. Capital R equal to small r. Capital R equal to small r, that's the condition for maximum power, and this condition is called maximum power theorem. Maximum power theorem. Yes or no? Now let me draw power versus capital R. Let me draw power versus capital R. Graph of power versus capital R. Evidently, when capital R is 0, power is 0. When capital R is 0, power is 0, as you can see. So power is 0 when, right? And notice that as capital R tends to infinity, this will be 0 and this will be infinite. That means power will be 0. Isn't it? As capital R tends to infinity, this will be 0, but denominator would be very large because capital R is very large. So power will be 0. That means if capital R is very large, then also power is 0.
It's like an asymptote.
And maximum power will occur when capital R becomes equal to small r. When capital R becomes equal to small r, you get a state of maximum power dissipation, P max. And the value of P max is equal to epsilon squared by 4r. Epsilon squared by 4r. That's the maximum power theorem. That's the variation of power with resistance capital R. Clear? Is that okay? Can I wipe this off? So, sometimes, a circuit could be more involved and there could be couple of loops that are coupled together. There could be a few loops that are coupled together in an electrical circuit. For example, there is a resistance R1, there is a resistance R2, battery of EMF epsilon 1. This loop is coupled with another loop, say this is resistance R3. There is resistance R4 and say there is a battery of EMF, say like this, epsilon 2. And I want to find the current through various elements, current through the two batteries and so on and so forth, current through various resistances, etc. This is a simple model, simple electrical circuit, and I want to find the current through various entities in this. I want to be able to find the current through various entities in this. Now, what I do is, say there is current I1 going this way, that goes this way, that current I1 passes through this, that current I1 comes to this junction J. This current I1 comes to this junction J, right? Now when it comes to this junction J, it has to now get divided. Part of this current will flow through this, the rest will flow through this, right? So then there is consequence of KCL, Kirchhoff's current law. Whatever enters must be leaving. So if out of I1, I2 goes away this way, then the balance I1 minus I2 must go this way. Yes or no? The balance I1 minus I2 must flow this way. How about it? Right? Now this I2 goes this way, it comes down here, it flows through this battery, this I2 comes here, and now I1 minus I2 is flowing this way. So I1 minus I2 comes here, I2 goes here. What's the total current entering this junction? I1, isn't it? This and this is entering this junction, so I1 must leave this junction. I1 must leave this junction. Yes or no? So what are my unknowns here? I1 and I2. I1 and I2 are my unknowns here. So I essentially need two conditions for two unknowns. I need two conditions for two unknowns. What I then do is, I take this loop and I apply KVL to this loop first. I apply KVL to this loop first, right? So then drop across this is what? I1 R1. That's a drop across this. Then I go from here to here. What's the drop across this? I1 minus I2 into R2. Right? Yes or no? And then from here to here there is an increase. So I'll say minus epsilon 1, minus epsilon 1. And this is algebraic sum of drops in this loop. This must add up to 0. This must add up to 0. That's K. No, if you like, I'll take opposite to the direction of current. If I take I1 like this, it will be like minus I1 that way. So then, isn't it? If I take an I1 like this and I choose to circulate the loop opposite to the direction of current, then I1 taken this way is like a minus I1 taken this way. Then I'll take drop across this is minus I1 R1. Then I come down to this, the drop minus epsilon 1 plus epsilon 1 plus epsilon 1 equal to 0. You do that, not a problem.
R2, that I1 minus I2, how was it distributed amongst the two loops? That I1 minus I2.
Oh, this.
So below, after R2, yes.
So I1 minus I2 is coming to this junction from this branch. I2 is coming to this junction from this branch. What is the total current coming to this junction? I1 minus I2 plus I2. That means I1 is entering this junction. I1 must leave this junction. So I1 leaves this junction.
I1 minus I2 will not enter that.
The net, don't think about that. What is entering, it is the net effect, right? Whatever is entering is equal to whatever is leaving. So I1 is entering, and therefore where will it leave? It has to leave here. So I1 leaves there. Got me? So that's KVL applied to this loop. Who stops us from applying KVL to this loop? Let's apply KVL to this loop. So then I have a I2 R3 dropping across this. Then there is a I2 R4 dropping across this. From here to here, epsilon 2 is the drop, plus, because there is a drop, so plus epsilon 2 is the drop, yes or no? Epsilon 2. Now I go this way, because this is part of this loop, right? Now I go this way. Now I1 minus I2 like this is like I2 minus I1 like this. So the drop here is going to be I2 minus I1 into R2. I1 minus I2 like this is the same as saying I2 minus I1 like this. So if I2 minus I1 was like this, then the drop would be I2 minus I1 into R2. That is 0. So now 2 equations and 2 unknowns, and I can solve for I1 and I2. I would then know the current in all branches of this electrical circuit. Not only that, there is nobody stopping you from selecting a loop of any kind. For example, I could have selected the outer loop. Not a problem. Let me apply KVL to the outer loop. Right? If I apply KVL to the outer loop, only for fun, this is the outer loop. What is this? I1 R1. Drop across this is I1 R1. Drop across this is I2 R3. I2 R4. Plus epsa 2 minus epsa 1, and this must be 0. Hey, now the fact that I want to tell you is this is not a new equation. In fact, if you add these two, you'll get this. If you add these two equations, you'll get this. So this is not an independent equation. You know what I'm saying? Nahi samjho baat. If you add these two equations, call them the principal equation, you'll get this. So this is not a new equation that you've got. It's essentially just a linear combination of these two equations. It's only a linear combination of these two. Now you can use 1 and 2, or you can use 2 and 3 to solve for I1 and I2, or you can use 3 and 1 to, you can use any two equations to solve for I1 and I2. You'll get the same pair of values of I1 and I2 because they're not independent equations. They are the same equations obtained by a linear combination of the remaining two. I could have taken a loop like this also, this way, this way, this way, this way, this way, any loop I could have taken, not covering a branch twice. I could have taken any loop, anyways, that's fine. It does not matter, but obviously, you don't want to complicate matters by selecting weird looking loops, right? You don't want to do that. So be simple in your approach. Select the loops that you can see with the white of your eyes readily, right? So see in this situation we've applied KVL as well as KCL. KVL we've applied twice, and KCL we've applied at this junction, and this junction we've applied KCL. Isn't it? At two junctions we applied KCL, and in two loops we applied KVL. Yes or no? Right now? Now, sometimes electrical circuits are also solved a little differently. Let me maintain the same circuit but give you a different way of looking at this circuit. Right? Can I just remove this and maintain the circuit? Right? Are you confused? Huh? I'll explain again. No? Sometimes we apply what is called Maxwell's loop rule. I'm going to teach you what is called Maxwell's loop rule. Maxwell's loop rule. What we do is, instead of taking current through branches, we take currents through loops and superimpose. I'll show you what. Earlier we had taken a current through this branch, and then through this branch and the balance through this branch. We took current through branches. Now what we assume is we take current through loops. There are two loops here, this loop and this loop. I assume a current I1 through this loop. This is loop 1. And I assume a current I1 like this. And then I assume a current I2 through this loop. I assume a current I2 through this loop. These are currents that I assume through the two loops. Right? Now, I'll apply KVL to this loop. So what happens is, when I take the resistance R2 as part of this loop, then there is like I1 going this way, but there is like I2 going this way. That means I'll take like a I1 minus I2 going this way. Yes or no? This loop is driving I1 through this resistance downwards, whereas this loop is driving I2 through R2 upwards. So when I'm applying KVL to this loop, then I'll take like through this resistance, I'll take I1 minus I2. You know what I'm saying? See what I do. If you're still confused, I'll explain. So these are loop currents that I've taken. These are loop currents. There is a subtle difference. Huh? There is a loop current that I've taken. So I apply loop rule to this loop. Drop across this is I1 R1. This is loop 1, I1 R1, right? Then across this, there is I1 going this way because of this loop, and there is I2 going this way because of this loop. That means there is a net I1 minus I2 going downwards. Yes or no? R2, yes or no? And then there is increase, so minus epsa equal to 0. Epsa 1 equal to 0. Right? That's loop 1, where I've applied loop rule. Now I take this loop. So there is like a I2 R3 plus I2 R4 and plus epsa 2. Now it's like this loop is driving I2 upwards and this loop is driving I1 downwards. So I can take this like I2 minus I1 upwards. Through R2, I can take like a I2 minus I1 upwards. So I2 minus I1 into R2, this must add up to 0. Yes or no? Now the merit in using a loop rule is that I don't have to bother myself about junctions. See, I have not bothered about junctions here. See, I didn't have to bother about junctions. So when there were multiple loops, you know, there could be a third loop, a fourth loop, a fifth loop. I can just take loop currents and I will not have to bear the headache of dealing with the junctions. So I can just solve for I1 and I2. The current from J to J prime is going to be I1 minus I2 downwards. If I1 minus I2 is positive, it's going to be downwards. If I1 minus I2 is negative, it's going to be upwards. And you can be arbitrary in your choice of direction or sense. Eventually, on solving the two equations, the sense will be revealed. Whether your choice was appropriate, then a positive number would be obtained. If opposite, then a negative number would be obtained. So you don't have to break your heads over that direction. You don't have to prima facie know what would be the actual direction of flow of current. You can be absolutely wild and irrational about your direction and sense of current that you've chosen. It's okay to do that. Okay. So now, my friend, I'm applying KVL to this loop. I'm going this way. So this is I2 into R3 plus R4. I2 into R3 plus R4. And then plus epsa 2. Now I go this way. This loop is driving I2 upwards. This loop is trying to drive I2 upwards through resistance R2. And this loop is trying to drive I1 downwards. So I can say when I'm circulating this loop clockwise, I can say it's as if there is I2 minus I1 going upwards. Huh? It's I2 minus I1. It's I2 minus I1 This loop is trying to drive I2 upwards, whereas this loop is trying to drive I1 downwards. So when I'm looking at this branch as part of my KVL, then it's like when I drop from here to here would be as if I2 minus I1 is flowing upwards. Got me kya? Sure na? I2 minus I1 into R2 would be the drop. No? Confused? Confused? No? So that's one clockwise, one anti-clockwise, both anti-clockwise, both clockwise. Nobody stops you from doing that. So sometimes when you are feeling weird, just be arbit and get that sadistic pleasure of choosing all wrong directions. There is no problem with that. Right? But the only thing is, at the end of the solution to the problem, the circuit will humble you. It will say, all right, you choose what you like, but I'll throw up my science as I deem fit. So you'll feel humbled. Your choice of directions went all wrong. The circuit still told you what was right. Right? So when you solve, you'll get the science along with I1 and I2 and be happy with it. Or be unhappy with it. Right? You understand the Maxwell's loop rule? And many loops, then you don't have to bother about junctions. That's the merit of Maxwell's loop rule. If you have to apply KCL along with KVL, here we applied two KVLs, but we never applied KCL. Right? And the merit in applying loop rule is you don't bother about junctions. You don't bother about junctions. You can be reckless with the junctions. Yes or no? All's good?